Hey guys, welcome back. In this video, we'll be talking about the PBR overall workflow and what PBR is and how how the whole thing operates between Unreal Engine 4 and Painter, well, Substance generally. Um, I was thinking of maybe doing this within the software, but there's a much better example online. I do recommend that you, so to speak, check. Um, the PBR guide of algorithmic, which is, by the way, we're going to be going through right now, just in a in a glancing fashion. I'm not going to go in depth. I recommend you go ahead and read through this stuff because it's highly well presented and explains everything that you really need to know. But I'm just going to glance through it so that you have an idea of what we're about to be doing in the next video. Anyway, here, this is the first and the second volumes, respectively. I just type Substance PBR guide in Google, and you'll get what you're looking for. Now, let me just make this a little bit bigger so that we can see a little bit better. Now, the reason that PBR is called actually physically based rendering and sort of shading is because it's essentially a physically based formula. In other words, it kind of represents the realities of life. In other words, it calculates light and how it reacts with different surfaces depending on the properties of these surfaces. So in order to understand how this whole thing works, we need to take a look at how light behaves. Now here, this is the first picture over here. That's the reason I'm using this guide anyway. Is as you can see, the angle of incoming ray of light is the same as the reflected light when you have a perfectly reflectable surface, in this case a polished metal surface over there. Like if you had a mirror, right? Well, a perfect mirror, not just any mirror. If you had a perfect mirror, whenever you shine a laser on one side, the angle of impact will be the same as the angle of reflected angle of the laser. So this is a fairly simple explanation, I think. So as you can see, there's also the normal for the material itself, in other words the mirror, and this is a fairly simple graph, so to speak. So this is how light behaves when it hits a perfectly reflectable surface. But as we all know, there's no such thing as real in nature as a perfectly reflecting surface. Therefore, we need to figure out how how objects react. Now over here you can see that there's a thickness map, and the thickness map essentially tells you how far deep can light be light get absorbed, so to speak. In other words, if you had a thick layer of skin, it will be dissipating light much more than a thin layer of skin, which might actually let some light through it. Okay, if we go further down over here, you can see that depending on the roughness of a surface over here, as you can see, smoother surfaces get much higher quality reflections, such as you can even see the sun over here, whereas a rougher surface, as you can see here, has much more thickness. In other words, not thickness, but, well, technically thickness, but in reality, this is just the micro detail on the object and how much light gets penetrates inside, and then the reflectance values are, randomized here because, such as you could have different problems, not problems, but irregularities on the surface. Okay, so this is an irregular surface. This is a completely flat and polished surface. Therefore, the reflectance values change depending on how much roughness there and how much roughness is available to the object. Okay, and here is a better actually version. As you can see here, this is your surface, this is your incoming ray, and as you can see, it penetrates deep, however deep it has to penetrate within your object. And since the denser packed the object, obviously the more light will be either absorbed or has to bounce out, and then it just bounces out from a random point out of the object. In other words, you will get the effect over here where, as you can see, a ray of light hits for example, the sun. We take this highlight over here, and it hits this object on this side. However, due to the roughness of the object, the light gets scattered around, and you don't get a perfect reflection. So I hope this is a fairly simple understanding. You got your ray, and as you remember, a lot of the lights, technically speaking, this should be the same angle when it comes to reflectance. However, as you can see, the surface over here is not actually flat, in other words, straight, or well, with zero roughness, so polished, then you'll be getting a scatter such as this. You're going to have some of the light being fully reflected, however in random locations, so it won't be focused, and then whatever light is left over will be spread out and distributed across the surface itself. You can think of it as paper, for example. If you take a flashlight and you flash it against the paper, you're going to have some diffusing. It would be better probably seen as a, well, not paper, but let's say thicker paper. Okay, so depending on the thickness of the paper, like if you have a flashlight and 3 types of paper in terms of thickness, and you just put that paper in front of the flashlight, you'll see that the thicker the paper, the bigger the blob of light coming out on the other side of the paper. That's the amount of light that gets actually permitted to go through the object. Whereas if you look on the other side, you will see that it gets actually bloated up, right? So, since the reflection, it will actually be a little bit less focused than on a thinner piece of paper. Oops, smashed my arm on the table here. Anyway, on the desk. Okay, so here's the microfacet theory, which is essentially, like I already said, the micro detail on the surface of a object. So as you can see here, we've got some irregularities when it comes to our surface. Here, the blue line represents the macro surface. So if you had a ball, for example, realistically speaking, you wouldn't really see these small things over here, right? These small cracks, the small irregularities. The topology of the object would be completely flat to the eye. However, on a microscopic level, you will always see these irregularities because, like I said, there's nothing in real life that is completely polished. Okay, there's always irregularities on any object. You can polish as much as you want. For example, if you take a sandpaper and you start simply sanding something off, no matter how fine a sandpaper you get, you can even get a 6,000 grit, 8,000 grit, 10, 20,000 grit, whatever floats your boat. You will always have a layer of irregularities. Now, granted, these could be very small and they won't be impacting the light source as much. Obviously, the more polished the object is, the less apparent and evident the existence of this microsurface will be. However, it always exists, so you have to understand that as well. Obviously, the bigger the gaps, the bigger the sort of microsurface mountains over here, the topology will create different levels of distribution of light. Since when something hits it over here, as you can see, it could perhaps block its own reflection. It could also, this is obviously simplified, but if you think about it, since this is light, or let's say this is light, and it could, for example, bounce off over here, and then it could bounce over here, obviously very small values. You have to understand that the amount of light reflected can never be more than the amount of light hitting an object. So this is essentially the law of conservation of energy. Anytime you shine a light on something, the amount of reflected of that light is not going to be the same amount as the input that you're giving it. So let's say if you have a flashlight or a laser, once it bounces off 20, 30, 100 mirrors, it will dissipate, not because the mirrors will absorb some of that energy. Whereas in a perfect world, it would be bouncing indefinitely. I mean, of course, if we put it in vacuum, not in air, where you could account for the air molecules getting in the way. Anyway, that being said, this is how the microsurface works, and you can obviously read up on all this stuff later down the line. So as you can see here, this is a very good example. We've got your little microscopic view of this object here. As you can see, it doesn't really distribute the light evenly. It's not a perfect reflection. So you see the highlight, but you don't really see clearly, and that is due to the fact that these rays of light, when they hit the surface, they get scattered around in different directions. And then when you add that with the fact that some of them can penetrate inside and then bounce out again, such as the green ones in this case, you might have a fairly complicated rendering model, which requires a serious amount of computation, which was not possible 20 years ago, for example, when the light, basically the how should I say it, when the technology was not simply available, right? Then we've got the color. So if you studied any sort of regular physics, you will know that the white color is essentially a combination of all the colors of the rainbow. And if you use a prism or some kind of a scattering crystal or something, you could basically scatter the light into all of its components depending on the the prism you use. In other words, since light is combined of all of these colors, the reality is that all the objects, for example, a red apple, will reflect only the red part of the spectrum. which means that like black, for example, absorbs everything. White reflects everything. Green reflects only the green wavelengths. Yellow only reflects the yellow wavelengths, or combinations of these colors. But you have to understand that none of these will always be, completely reflected. You could have some combination of red and green, or blue and purple, or even purple and orange, depending on the color of the object. But every object has a particular absorbance value in the material it's being covered in. So some materials absorb almost all the rays, some materials absorb very little of the rays, such as white stuff. So the brighter the thing is, the better it is at reflecting a particular color wavelength. So your t-shirt, for example, is bright red. It's much better at reflecting the red color than a dark red t-shirt, which mostly absorbs almost all of the light spectrum, which obviously creates the conundrum. Well, if I see something that is red, is it really red, or is it just reflecting red, and why is it red? So it creates this interesting dilemma. You could think of it on its own, but as you can see, it's a fairly simple explanation on how it works. There was a physical term for splitting the light into its components in terms of the spectrum. I just forgot it right now. It was something cool, but I forgot it anyway. Then you've got your different algorithms for calculating how light gets scattered across the roughness. Obviously, Blinn specular distribution was the original initial calculation method. After that, you've got the GGX, the whatever it's called, this function here. You can actually take a look at it later down in this section. I'm not really going to talk about this very much because, well, as a creator, you don't really give too much of a shit how this whole thing gets calculated in reality. Very few players will actually notice differences between the two. However, it's nice to know that this is a much better, the newer versions is a much better representation of the method of light calculation. Okay. So here we talk about the energy conservation, which is exactly what I said before. Then you got the Fresnel effect. Now that's a very interesting factor, by the way. If you think about it, the Fresnel basically explains that I think it was a French guy. Was it a French guy? Yeah. So Augustin Jean Fresnel. Anyway, what the French guy said and observed, obviously improved, is that the closer you get to a normal of the viewing points, so let's say the light reflected incoming is dependent on the angle at which you view your object. So as you can see, this is a glancing view, and therefore you will be able to see a lot more of the reflection, whereas the normal over here, which is basically dead on, the F0 in other words, is going to reflect much less, simply because there's less light hitting it from this point. And you can think of it as the viewing angle of your monitor. Obviously, if you take a look at your monitor from the side, you will see a lot less clearly the picture. You'll start seeing reflections, and it's actually a big part of monitor selection when you're purchasing stuff, such as it's not only its refresh rate, but also the viewing angles, and it used to be very small in TFTs. Now it's nearly, I think it's 89, 87, 88 degrees. So this is not really an issue in these days, but it used to be a big deal, when these monitors first came out. Of course, maybe you're in the future and you're looking at this, you're watching this video in a hologram. So in that case, you're looking at a pretty archaic video series. But most of these things should apply still, since this is the most accurate representation of the real world, seeing as it is physically based. And last time I checked, reality isn't going anywhere, so this is exactly what we need, and probably going to stick for the rest of game development history, since there's really no better way to represent reality when other than sampling from reality. Anyway, just so you know, this F0, which is the Fresnel 0 at 0 angle, basically reflect its, how should I say it, depending on the surface or the material that this angle is corresponding to, you may have different results in terms of reflection. As you can see here, anywhere between 2% and 5%, depending on what it is: plastic, wood, concrete, brick. There's obviously more differences in terms of reflection values, but you can define the material at this F0 value, since most of the time players will be looking at your objects face on and head on. Anyway, we can go further down the line. This is the Fresnel reflectance in degrees. You can calculate this stuff yourself if you want, or read up on how this is calculated. A lot of these values, by the way, are actually real life sampled. So copper, iron, aluminium, silver, all this stuff is, like if you take a material, for example, in Substance Painter, and it says gold, this gold would have been sampled and assign the sRGB values that will correspond directly to the physical gold in real life. So this is the real color, or in other words, the albedo of the gold. So you can rest assured, including its reflectance value, etc. Therefore, it's important that you better use the materials provided, there's stuff like titanium, etc. So you really want to be having a how should I say it? Physically accurate model, of course, unless you create some kind of fantasy universe and there's different materials in there, but then you're going to need some fancy stuff such as, I don't know, maybe glyphs or some kind of energy levels running through it, whatever. The point is that when it comes to base color, this is what you will be working with. Obviously there's more than just these 5 over here. Same goes for plastic, but it's not as there's not a lot of deviation when it comes to these are essentially the reflectance values of plastic, rusted metal, water, ice, and glass. They're not reflecting very well, whereas gold, silver, aluminum, these are fairly polished metals and they reflect pretty well. And glass, even though you might think that it's reflective, it's not really. It lets stuff through. That's why it's used for mirrors, right? In a mirror, you'd have a piece of glass, and then behind it you'd have like a piece of foil or something, which would usually be aluminium or something that would reflect the light. Just it's glued onto the mirror in order to protect it and keep it stationary, so the foil doesn't collapse or anything. Anyway, now that we've talked about the F0, in other words, the Fresnel over here, since it's important, I would really recommend you read through all of this stuff. I'm just not going to go through it because we got 2 volumes that we're going to go through. We also going to need to talk about metals and non-metals. Now, in terms of metals, obviously, like I said before, as you have something polished, even though you can't possibly have 100% reflectance, well, if you could, but that's just idiotic. As you can see here, the reflectance values change, the angle of reflectance changes depending on your reflectiveness, and obviously you don't get a perfect reflection, it gets split up. And then you've got the light that's being absorbed or reflected, in other words. So if you remember the red apple analogy, in this case it will absorb this wavelength over here. So reflect only this wavelength. In other words, it will provide this orangey yellow color that you see over here. Then you've got the map itself. So here's the real interesting part. So how do we map this stuff? Now, if you remember correctly, we've got a material that needs to represent a particular set of physical properties. And in this case, we've got metal and a base color. Now, when it comes to the metal, you can see that it's a grayscale. So this just shows the shader or the renderer or whatever that, this is like a mask. And it says where you're going to get raw metal and where you're going to get rust. Now, in this case, the black bits are completely non-reflective. In other words, they're dielectric, so they don't reflect pretty well. In fact, they almost reflect nothing. And then you've got the raw metal, which reflects very well, and you can see a lot of stuff. As you can see, they got different F0 values, and that directly corresponds to their reflectances. So this is the color, which will be feeding, basically you put this stuff on top of the color so that you see how color reacts based on these values over here. And as you can see, this is the result. Obviously, these values range when you got metals and non-metals or even gemstones. And depending on the workflow, you may or may not have the ability to change these values. By the way, all of these values are represented in linear space, meaning that you need to have from 0 to 1. You need to represent every color, into red, green, and blue in linear space. And then you need to, once you have it represented, you need to actually convert it back to, 255. And that's what Substance does for you. So you don't really need to think about it that much. Right? Now, there's loads of other stuff to read about this, such as oh, there we go. This is what it actually says, linear space rendering. You can even read about this, and this is just a small explanation of what it is. But linear space is basically like normalized space. All right. So you can see over here, you've got your key factors. It's very well presented, tutorial. I highly recommend you not only read these these documents over here, but you also go over the algorithmic documentation, even go through their tutorials, since they're much better presented than, I'm capable of. Not to mention that all this stuff as well that is referenced, you can easily just click on it and see, basically see what this has been pulled off. For example, the microfacet models, defeating a physically based shading model, whatever. And you got an introduction to BRDF models by Daniel, this guy. right? So definitely take a look at this. I highly recommend, again, you check this out. And that being said, we're going to go over the actual workflow that we'll be using. In this first guide, obviously, you can see that we've got simple explanation of what a Fresnel reflectance value is, and what how lighting is computed, etc., etc., etc. Then here we're actually going to be talking about how this whole thing works with our engine. Now, there's two ways to represent this stuff. If you take a look over here, you've got a metal roughness workflow, which is the workflow that Substance uses, which is more widely adopted and is used by Unreal Engine 4. And then you've got the specular glossiness, which is used by Unity. Now, we're not going to go over the specular glossiness because I'm not going to use Unity, and if you do use Unity, this is not the right video series. There's plenty of other tutorials about Unity, so this is where you should split off and splinter into Unity territory. But since we'll be working with Unreal, I'll be sticking to this top bit. Now, by comparing these two, you will see that they use a different set of maps. Both use kind of the same thing, such as diffuse color in this case. However, they are inverted. Now, results are pretty much identical, as you can see over here. There's really not that much difference in terms of the results. However, you will see that there is a difference in terms of maps. So the roughness, the darker regions, represent the rougher areas, whereas the brighter regions represent the less rough areas. The glossiness bit is inverted. So as you can see here, the glossiness is essentially the opposite of roughness, which is pretty cool, I suppose. So that they're fairly easily interchangeable, and you can convert all of these in Substance. There's no big deal. You can have something with a diffuse glossiness and specular and convert back into base color, glossiness, and metallic. Now, both of these workflows, of course, use the normal map, the ambient occlusion, and the height maps. So that is completely fine. Obviously, they can use a thickness, I believe. So that's not a big deal. The only difference are these three maps. There's also a difference in terms of size. You see, metallic roughness is a more compact method of working, since it only has grayscale maps, with the exception of of the base color. Here you've got well, look, the point is we're not gonna go into specular glossiness anyway. So I just wanted to say that technically speaking, metal roughness and specular glossiness have no real distinguishable differences, except a few minor issues when it comes to textile density. And generally speaking, metal roughness is a much more compact method of working, where the specular glossiness uses more channels. It's got higher map density in terms of its weight. So you can have a material that is, this material could be, if this material is 500 kilobytes, this could be 750, 800. That's not a big deal, since there's plenty of space available to players. But there's just one thing to consider, because this does get loaded into memory. So you have to think about that as well. Now here we can actually, it goes about what, PBR, this and that. By the way, the cool bit about PBR is whenever you have a metal defined, it will behave the same way across different platforms. Most of this, for example, this particular material will perform, will be viewed differently depending on the environment and not depending on the maps available, which is really cool bit, because you can interchange. You can have the same material taken into a cave, and then from a cave into a busy street, and then from a street to space, and then from space to another planet, and then from this planet back on Earth, for example, or any other planet in a spaceship, right? So it will behave differently depending on the light sources available. It will always react accordingly, and will always look sort of realistic, especially when you got it properly set up. And there's one thing about it, is that properly setting up these materials can be challenging, since some values are restricted. In other words, when you got a metal, you need to be careful not to have it completely reflectant. Even if it's a mirror, it's not a perfect reflection value. You might get errors with particularly bright lighting conditions, or maybe too low lighting conditions. It will reflect too much. So in this guide over here, you will see at the bottom there's appendixes about how much, what kind of values you need to have. All right, in terms of, to get proper results from your materials. Anyway, we can go further down here, because there's better pictures over here we can talk about. Now here's the metal roughness workflow. Essentially, you've got two things. How should I move this? Essentially, you've got two things, which is your base color. This base color should have no lighting information at all. It should only have really basic color. And this base color will, by the way, define the reflecting color of your metallic layer. So that this is actually a grayscale, therefore it has no color. And if you want it to have a particular color, you need it to be mapped to the base color. So this kind of, goes on top of it and reflects whatever color is, represented here. Much like with the red apple, if you carved a couple of bits into the red apple, it would no longer reflect the red light and will reflect the fleshy yellow bits or white bits or whatever the inside of the apple is. You get a wormy apple, it could be warm, could be brown. And then of course you got the roughness, which basically denotes the microsurface, values here. So it basically tells you how much light is scattered even when it is reflected. As you can see here, there's a lot of dirt, and this is basically a roughness, right? How much dirt and grime you've got on top of your material and how it behaves based on that. Therefore, if you didn't have this roughness, these highlights here would probably be much more pronounced. Okay. Right. Obviously, as you can see, the metallic bit is obviously the black stuff is non-metal, the white stuff is fully metal, and anything between. It's just a grayscale, right? Okay, we can continue further in now, and this is the height map over here. As you can see, you've got two different ways of using it. You can get a map and essentially map it to use it as basically get ambient occlusion out of it, as well as a normal map. Look, as long as you got a height map or a normal map, you can convert or grab or extract or just create different maps based on this data. And as you can see, even though this is a completely flat cube, since it has height and ambient occlusion, it actually looks very detailed. And as you might imagine, this saves a lot of how should I say, polygons. Obviously with polygons this would be much heavier than just 4 faces, well 6 faces in this case. And it's fairly effective too, especially since ambient occlusion provides the needed depth in these cracks over here. As you can see, there's this sort of just more pronounced shadows in the cracks that are being created by the height. Otherwise you won't be having that. Obviously a normal will also greatly improve this, since a normal also responds, it helps with light calculation, provides a little bit more detail when it comes to your object when you textured it. Now, let's talk about the reflectance value of the dielectric. Remember, we've got the same bit over here, which is the black surface, which is the paint, essentially, in terms of its color reflecting. And as you can see, it has a particular reflectance value. In this case, 0.04. It means that this is like paint, all right? It's not reflecting very well. So there's virtually no reflection, actually, if you look at it closely. There's pretty much no reflection here at all in this red stuff, whereas there's plenty of reflection here. As you can see, there's highlights on this side, right? So that's cool. Then you've got the the same explanation about your Fresnel, etc., and how they differ. Gemstones, for example, would have something like 5 or even further. But there's some cases where we might want to change that, and it is possible, however, not in Painter. You need to go into Substance Designer, and you will be able to change that using a node. I think over here, yeah, you can use an override F0. And it will allow you to select a particular, value if you want to have, hands-on control of what it is you're making. Chances are, in our case, we're not going to have to do that, especially since I won't be going through the designer process, right? So you just read this to be informed, and if you have designer, just play around with it. Then you've got your base color, which is a standard red, green, and blue color range. Difference being that red, green, and blue could be represented in different ways, but the standard bit is from 0 to 255, of course. And then here you've got different values on it. As you can see here, the base color map is an sRGB map which contains 2 types of data: reflected color for dielectrics and reflectance values for metals, as shown in figure 0.07. So as you can see, there it is. You've got your reflective diffuse color for dielectrics over here, and then you've got reflecting color for metal, that's why albedo is important. It's also known as albedo, base color. It has no reflectance information on it. It's simply base color. That is nothing else. Simply it denominates what wavelength would the object reflect if it were to reflect it. Okay, so that's important. So you have to understand that. Here it is. As you can see, there are some cases where you have to stay within certain ranges, especially when you got rust and stuff like that, which are oxidized dielectrics. Which means that rust does not reflect very well, okay? And as you can see, we've got the correct values or two dark values. There's definitely, these are basically flat down to 0, as you can see, if this is too high of a level. And as you can see, there's a strict range between 30 and 40 and 240, or 50 to 240, which would be the the stricter range, as you can see here. There's also a utility. This green bit here, as you can see, is a utility in Substance Painter. Usually you do that at the end of your asset creation or sort of texturing, which basically shows you which, where do you have your values too high, and if you do, where you're going to expect errors to happen. As you can see, there's definitely a fairly pronounced point here. Of course, you might want to say, well, artistically speaking, I want to have this so exaggerated, but at the end of the day, this will behave differently depending on the environment, and it's just very difficult to figure out how it will behave if there's too bright lights or not enough light. Okay, so I highly recommend you use this tool at the end of your creation, which we will probably do on our own in our own project, since, for example, we will be using skin and it is a dielectric, so we want to be not having our ranges too high, right? Now you've got the same thing over here, which is their base color micro occlusion. I never use micro occlusion. I think it's a little bit too like too overkill. Just use normal maps. But whatever, whatever floats your boat. And as you can see here, you've got your little setup. So you've got dark values should not go below 30 sRGB or 50 sRGB, which is a strict range. 30 would be the lowest you would ever go. And brightness should not go above 240 when it comes to metals. When it comes to non-metals, right, in terms of reflectances. And you can see the reflectance for raw metal is going to be high in the range of 70, 100, and which you cannot map to further than, well, you can map it to the max, essentially. But don't make it reflect. Look, most of the time you don't want to have 100% reflectance, all right? Okay, when we go further down, as you can see here, you've got your metallic values, which are we're going to be talking about the dielectrics here, which is the rust in this case. As you can see, there's definitely a lot of garbage on top of this object, and you're going to have your metallic map represent that. As you can see, this is the metallic bit, fully reflected color when it comes to that metal. This is iron, I believe, so... obviously, this is pulled from the database, which is physically sampled and properly aligned to represent iron as as closely as possible. So this is your color over here in terms of reflectance, and then you've got the creation guidelines, which is pretty cool. So for raw metal, you've got to go from 70 to 100% reflective. You use one of these colors, and it has to be however many in terms of sRGB. So this is what it is: 245, 246, and 246 for aluminium. Obviously, you'll have to ask yourself, well, if you're doing something, is it metallic or not? And this is very simple, I think, since everything you do will have some kind of definition. Oh, is this plastic? Is this a metal? You can also think of fully reflective mirrors as metal, since, well, they are made of metal. There's no such thing as for example, water would be an interesting bit, by the way, since water is reflectable, but not that much. So it is technically, it has some metallic properties, but it is also a dielectric. Like water is a difficult material to make and also properly represent. So I wouldn't be an expert on that. Well, I'm not an expert on anything, but I really wouldn't know where to start when it comes to water. I mainly use other people's, like Unreal Engine 4 stock water materials, or just outright buy one, since making a water material, especially a believable water material with flow maps, etc., is very, 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 very difficult, at least in my eyes. I'd rather prefer just to program stuff. Anyway, as you can see, you got a corroded or dielectric layer, such as the rust in this case. And as you can see, it's represented on the base color. And you got the paint, which is dielectric. Both of them are dielectric, but since the rust is like a different color set, you need a different approach to it. All right, and as you can see over here, you've got also a dirt layer, which is represented in the metallic map, since dirt is not metallic and therefore will, it will not reflect light. Now, in this case, they're talking about not accounting for stuff. So as you can see, you got loads of errors. So you need to map this away, such as you can see right over here. Let's say you have a metallic map and you add the dirt, but it's not accounted for. So in this case, it will be reflecting like this these are reflectance values which are not accounted for. Here you say that they're not metallic, so basically you add a metallic channel to whatever you're painting or add it to the mask, and it will say, okay, so this is non-metallic and therefore it will reflect less. Okay, obviously it's not going to be fully non-reflective, but I hope you get my drift. Now here we're going to be seeing basically how how these maps look like. Honestly, just this is how to do this stuff in Designer, and this is a Designer chart. So look, don't worry about that bit. This is just you can talk about this in the future, or you can just find this out on your own when you use Designer. And there's some tips here, like if metal map has values lower than 235, then the reflectance value needs to be lower than base color, right? So there's that. And then you've got the roughness. It's obviously also a grayscale linear, and here's the same picture that we've seen before. So as you can see, the roughness represents how much the here's the smooth. It also explains to you like this is smooth completely. The white stuff is fully rough, so it doesn't. Oh yeah, I had it inverted. My bad. Obviously the specular glossiness is the inverse. So this says how rough an object is, whereas in the glossiness side this is inverted. So the black would be rough and the white would be smooth, and would represent essentially how so to speak, how how glossy an object is, so how polished it is. So anyway, I hope this is fairly self-explanatory. I'm not going to go over this again. I hope you understand. This should be pretty simple to grasp for now. Now here's a little bit of an issue when it comes to metal and gloss. Metal and roughness workflow, and that is, oh, what do you know? If you hold shift, it'll actually, that's pretty cool. So as you can see, you've got artifacts here, and this is mainly due to several reasons. First of all, you'll always have artifacts in your edges, simply due to the fact that since this, as you can see, this is white, which is the completely rough bit, and the black, which is the completely smooth bit. However, in this case, you will see white artifacts in your edges. Now, this is a byproduct, of course, and it can be fixed by increasing your textile density, in these areas. Therefore, you need to have a proper, UV distribution. So that's where your UVing comes in when it comes to, correct, texture mapping. Now, obviously, zoom in close enough, you'll always find issues, and that is completely fine. But the higher the quality of your map, and the better the distribution of your textiles in terms of in terms of your UVs, basically always aim for square textiles, right? Remember the square checkerboard that we used. Aim for square, right? Since otherwise you'll be having these issues. And obviously, the more densely packed these squares are, the better it is for your final product. Depends, of course, how close something is to your player. It's very unlikely that a player will be zooming so close in to see these artifacts, but they will be much more pronounced if you have a lower resolution as well. If you got like something like 512 by 512 and a very badly made UV, this will be obvious. As you can see over here, that's exactly what it says. By the way, this is the inverse problem with the specular glossiness workflow. Of course, it's not as apparent because it's black and it's harder to see, since it merges better with the color over here. It's not as pronounced versus the white, which is over here. As you can see, it's much more pronounced since it's white. Okay. Now, it doesn't really matter since we're not going to be going over this, we're not going to be going over this right now, but as you can see, this is much more pronounced. If we just compare these two, this is the specular glossiness, and this is the metal roughness. Jesus Christ. I really need to uninstall this thing. I'm not using this anymore anyway. As you can see, much more pronounced. So in order to fix that, you want to have a better UV distribution and just higher resolution in terms of your, UVs. Sorry, your textiles. As you can see, actually, there's a good example of this stuff. This is obviously exaggerated, but this is your good textile density, right? As you can see, the proper UVs. These are how the UVs look, by the way. So this is the UVs, and this is the thing with the light. So as you can see, there's much of a difference. And then, of course, you've got the same thing over here, which are ridiculously small UVs. Therefore, you'll never have that. Okay, like you have to be a complete idiot to map something like this, right? This is obviously an exaggerated problem, but it will happen. It's still not as big of a deal. Like, you can have a little bit crappy UVs, but as long as you utilize your 0 to 1 space properly, you should have, Jesus Christ, you should have a, how how to say, a fairly well textured object. Obviously, don't try to texture something huge, which is like imagine if you had a spaceship, right? And you try to cram all that spaceship, like a huge spaceship compared to the overall world, let's say 200 meters by 200 meters in size, and you try to cram all of that inside this one space. Yeah, that's not like you're gonna get very shitty results because you're trying to wrap. Like if I were to use an example, take a, you know what? Think of it this way: if you take a napkin, what can you wrap inside that napkin? Because this is your napkin. The 0 to 1 space is your napkin. Like unfold it, right? Or don't unfold, whatever. Point is that it's a finite space. Technically, it isn't a space because on a napkin you can draw a car on a napkin, right? And it will be a fairly small car. Now, if you decide to color it and whatever, it's not going to be very detailed. Since if you stretch it over an actual car, you're not gonna get a lot of detail in it. Okay, so as you might think, a napkin isn't big enough to stretch over a whole car, but it is big enough to stretch over, let's say, something like an apple. So if you wanted a car on an apple, you could just plaster that napkin, wrap an apple in it, and that apple will have a car with fairly good details, since the object itself is pretty much pretty small. Either that, well, obviously the napkin is not your 0 to 1 space; it is the maximum size of a texture that can utilize that space. Okay, so the UVs are simply coordinates from 0 to 1. They're normalized, they're infinite. Okay, the problem is your texture itself, right? It could be 1K, 2K, 4K, 8K, it could be 16K, right? Whatever. But obviously, the higher the resolution, the more stuff you can cram in the 0 to 1 space and have acceptable results. So just think about it, think on it, whenever you're making your UVs, so that if you decide, let's say, well, I'll be using 4K, so I can get away with cramming a lot more stuff in my UVs for details with objects with less details. So just make sure not to go overboard, and think about it when you're doing it, right? Okay, that's why I wanted to talk about this, since this is the time now for you to fix up your UVs if you have a problem with your UVs, since if you do have a problem, you don't fix it up, they're going to become apparent when you're texturing, and they'll be definitely apparent in the game. Okay, next, of course, we got the pros and cons, and as you can see here, they're fairly simple. You've got your, can be easier to author. You've got your less memory texture memory, since metallic and roughness have both grayscale maps, unlike the other ones. The specular glossiness, and then you've got, of course, it's a more widely adopted workflow, meaning that if you share something to someone else, he won't have to convert it back. He won't have to convert it into specular glossiness, or basically it has it's more widely adopted, right? Just it's a pro. Now in the cons, of course, you don't have control over the F0 values for dielectrics, but of course that is also remedied by just going into Designer and just adding a override for your F0. You've got your edged artifacts, which are more noticeable. However, like I said again, these artifacts are mostly, you'll be the one responsible for them, especially if you have UVs that look like that. Okay, now you've got the specular glossiness workflow, which we'll be completely glancing over, since this is it's basically a different workflow that we won't be using. So if you're really interested, just read the damn thing yourself. Okay, specular glossiness, blah, blah, blah. And this is the comparison. No, it's not the comparison, my bad. Where's the comparison? There used to be a comparison. Where is it? There we go. Oh, no. We're back in metal roughness. Why are we back in metal roughness? It's the same example anyway. Even in specular glossiness, you don't want to be having that. In both situations, you want to have good UVs. So if you say, well, I want to have shit UVs, I'm going to use specular glossiness, you're not going to get better results at all. Okay, so let's see. We got our pros and cons. Obviously, edge artifacts, so that's less apparent, and control over dielectric F0 and specular map. Now, here's the cons. Because the specular map provides control over dielectric F0, it can be more susceptible to incorrect values because you don't know which is which, right? And it's possible to break the law of conservation, meaning that more light gets reflected, or same light gets reflected from an object than when it impacts it. Then it utilizes more memory because there's one additional sRGB map, and then it can be more confusing to use similar terminology, blah, 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 blah. right? There's also video walkthrough available over here. I highly recommend you watch this stuff because it's much more in detail and much better presented than me. You know, instead of just going through a document, Wes actually created a presentation on PowerPoint like actual professionals do, not like plebs. You know, but since we're just glancing over this, I wanted just to take a look at it. Then you've got your ambient occlusion. This is also very well explained how ambient occlusion works. So it's pretty cool stuff, right? So Unreal Engine 4 have some pretty nice screen space reflections to simulate local reflections, but it's also nice to have your AO map. You don't need one, okay? You don't need one, and you know, to get good results, but once you use them in conjunction with the screen space reflection, you get ridiculously well presented objects because the detail in there will really be popping, okay? As you can see here, it only affects the diffuse contribution and should not include the specular contribution. In other words, it only says how much light gets diffused inside cracks, etc. Now, the AO creation, you can convert it from a normal map, from a height map, from pretty much any map, really, because you can convert normal into height, height into normal, height into ambient occlusion, height into thickness, normal into thickness. As long as you have a normal map, even if you have a height map, you're golden, okay? So the moment you have something on black and white, you're good to go, right? By the way, you could also think of it as a bump map because, like I said, a height map is better used as, a height map is a bump map used for terrain, right? Even though they represent the exact same thing, it's kind of, well, look, whatever, just think of it, we already talked about maps anyway, right? Here is the bitmap to material, by the way, a very powerful tool which allows you to take a picture or download a picture of whatever it is you want, and then you can create a material which is the exact same thing. So, you know, that's pretty cool. You've got the height here, as you can see. This is without the height map, and this is with the height map. We already talked about these different, you know, methods of fooling the eye in terms of, you know, in terms of the, you know, these maps. But the difference here, by the way, is that while you're painting a height map, and like I already said before, bump maps, height maps, bump maps, they don't actually play a role in light calculations. The reason this actually plays a role in light calculations is because it's automatically converted into a normal map, and then, you know, these calculations are basically added. Okay, so you have to understand that. So instead of painting with a normal, by the way, it's much better to paint with a height, because while painting with normal can be a little bit confusing, but when you paint with height, in other words, an alpha map, which also is, by the way, smaller in terms of size, so it's not going to be clogging up your hard drive. Well, hard drive, it's not going to be that heavy, which will also be, by the way, incorporated into the normal. It's simply much better to use. That's not to say you can't use a normal, but height map is the preferred method of adding detail, and since it's going to be, you know, recalculated in terms of light and normals, etc., it's going to be just fine. All right, and also it works with parallax mapping, which we talked about. Now, if you decide to create a set of steps like in Mass Effect, you know, and just fool people that there's steps there using parallax mapping, sure, by all means, but that's a little bit overkill in my opinion. But then again, they were probably optimizing for consoles, and those things are completely useless pieces of tech. Okay, then we've got the you know, how to make these. So as you can see, you can convert a normal into height, and obviously vice versa. This is how you would create, you know, this height, for example, from the bitmap to material, and all these different parameters. There's a whole set of tutorials for this. We're not going to be using them, by the way. And then you've got the fact that you can paint height. This is the initial object, and then once you just keep stamping these things, you know, you're going to get this highly detailed door. So in this case, there's actually a whole video series on how Wes creates this door using all of the tools available. So he starts from this in Maya, and then bakes the maps in it, and then paints the stuff on top of it, and, you know, adding different materials such as, you know, blue pipes or like plastic, whatever, paints, etc., and then you get a final product, like a final asset. I highly recommend you watch this. Obviously, it's much better presented, much better done and explained than I did. But then again, it's also a lot longer, in my opinion, since, well, maybe it isn't. It's about 3 or 4 hours long. I don't know. I recommend you check it out anyway. Right? And then you've got, of course, the normal map, which we already talked about. It simulates surface detail, and it's the same usage across every workflow. Okay. Still, I recommend you use it in any situation, since normal maps are very important to have. As you can see, you can convert from a height to a normal map and vice versa, and this is the result over here. You can use a bitmap to material to create no map. Look, as long as you have one map, you have every map. Just think of it this way. You can even create AO out of normal maps. Just any map will anything, as long as you can start from somewhere, you can do everything else. Obviously, it's better to bake a normal map. In other words, project it from a high poly object into a low poly object, and you get the baked results. But it's not impossible to extract it from something that already has surface detail and you just want to replicate it, such as this case, for example. Then you've got the utilities, and this is where the utilities come in handy. You've got your, well, the bitmap to material 3 is pretty cool. But if we take a look here, where is it now? Where are you? Look, there's another link to a video guide. Again, highly recommended to check it out. Substance materials, blah, 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 blah. GameTextures.com, that's pretty cool. Wow, that's pretty cool. I didn't even know that. I actually never read this bit since I wasn't interested in this side. But as you can see, yeah, you can go to GameTextures.com. You can download extra PBR substances with your account. That's pretty cool. I actually will check it out after I finish with this video. You've got the reflectance values here as well. But when it comes to, this is just guidelines so that you don't fail at what you're doing. And this is the correction bit. This is the most useful bit anyway, since you might want to be just validating your stuff. So as you can see here, we've got some issues when we apply a metal rough material. This is a smart material created by Wes, I think. I believe they might incorporate this as an actual tool in the future, but for now it's simply, I believe it's in the tool set or somewhere in Painter anyway. You can find it if you Google it, but it shows you when your values are over in terms of sRGB, where you have too much or too little reflectance values, right? All this stuff. So whatever there's red, you got a problem, you got to fix that. Whenever there is green, obviously that's fine. As you can see, there's the same thing with the color safety. There's different. As you can see, these are corrected images. This is the correct range. This is a little bit too dark since there's no color here at all, whereas here you'll still see some color when it comes to your sRGB ranges. Okay, and then you've got conversion, which, as you can see, the roughness and the glossiness are just the inverse versions of themselves. You've got the base color. In this case, the diffuse only has, basically the specular is an sRGB color. So in this case, this is actually a very good example of the difference between the two. So as you can see, the color comes only from the base color, and everything else gets layered on top of it to calculate the final result. Whereas in this case, your color, so like the final output of your material, is split between these two objects, right? As you can see here, you've got the diffuse, which reflects, for example, the like the rust, right? This is the color of the rust, and here in the specular, this is the color of the metal, right? So, well, not the color of the metal, but like both of these, it's just heavier, right? Anyway. Point is, you've got your different charts here, and that's actually pretty cool. So as you can see, there's a little questionnaire which you can ask yourself, and it's fairly simple, really. Is the surface a metal? And then if it is a metal, you use that. Well, your base color has to be this and this and that. Your reflectance values have to be between 70 and 100% specular, and then it have to be between 180 and 255 in terms of sRGB. Obviously, use your provided real-world measure values, and obviously account for your dirt and metal. After that, you've got in if it's not a metal, you've got all these limitations over here. I actually recommend you print this out, since like I don't remember this, right? I actually have it written somewhere. Yeah, I have it written somewhere, but I didn't realize actually there was a little chart over here. I would print this. It's just a much better thing to have, since it allows you to quickly glance over and say, okay, so this has to be 30 or 50, right, or this and that. And obviously you've got your dielectric reflectance, which it's usually hard coded in our workflow. And if you really need to change it, you could just dive into Designer and change it. This is the specular glossiness workflow, for which I don't give a shit about. And then, of course, you got the reflectance values, which represent different things, such as in this case, you've got the reflectance values of water, which is a dielectric. Well, yeah, it is a dielectric, so it doesn't really reflect light in that case. It mostly just, distorts it, refracts it. There we go, freaking refraction. But as you can see, all these values are available here. Now, I believe they're hard-coded indeed in the regular workflow, and as you can see, the ranges here are between 40 and 75 sRGB, and in the metal you've got from 180 to 255, and these are the different ranges. This is where iron stands, cobalt stands, aluminum stands, silver stands. Somewhere here you got titanium as well, because you can't live without titanium. You need titanium. Titanium is the answer. All right, and if you, of course, as you can see, correct, incorrect comparisons. You've got your dirt layer problems where you didn't account for it. And as you can see, you've got the bit here where these are your issues, and they're basically not, named over here. Okay, this is the correct stuff for the specular glossiness, which we really don't care about, and that's about it. Yeah. So I hope I just was a quick glance over these two documents. They're very short anyway. There's only, like in this case, this is 31 pages. Realistically, 25, maybe even less in terms of the stuff that you need to read. This has only 13, so it's not a long read either. So I recommend, again, you not only read it but also watch the PBR guide that Wes created in a video format. And maybe I got something wrong. Maybe although I doubt it, but he will go a little bit more in depth than I did. Okay. Right, that being said, I think we're done with the theoretical aspect of it, and in the next video we will talk about the the tools available. We'll import the lower version of our worm, which is like the shitty version with the shitty UI, UVs, so that I can display the reason I wanted to cut the UVs there. The reason I cut the UVs the way I did anyway, and we're gonna experiment on that worm. All right, since we're not gonna be using that worm, it's the perfect target for that. And then we will go into Unreal Engine 4, sort out the import settings, create a pipeline, maybe add the import folder to our version control engine, in other words, Perforce. And we might even go over how to ignore different not only file sets but also paths from from version control. You can omit them. Anyway, that being said, guys, I'll see you next time. Bye bye.